Hello, and welcome to this GCSE Physics revision video looking at domestic electricity. This is the electricity supplied to our homes or our schools. We're going to look at how electricity is delivered to us, as well as how we can calculate measures such as electrical power, energy, and efficiency. This video follows quite nicely from an earlier video in the energy series. It's the third one in that series about energy resources and how they can be used to generate electricity. As we saw in that video, electricity can be generated by rotating a coil of wire inside a magnetic field. The current generated using this method is an alternating current, which means that the current flows in one direction before stopping and reversing. The current continues swapping directions backwards and forwards, changing at a rate of 50 cycles per second. You can see the voltmeter needle in the diagram here, moving backwards and forwards as the potential difference switches from having a positive value to a negative one. You can see from the graph of potential difference over time how the potential difference varies from positive 325 volts all the way over to negative 325 volts in the UK. This alternating potential difference between the two wires is then led to homes via the national grid. The blue neutral wire is earthed, so is at zero potential difference between it and the earth. The brown live wire is the one whose potential difference varies from minus 350 volts to positive 350 volts between it and the earth at 50 cycles per second. A third wire, the green and yellow earth wire, is included to act as a safety system. If an electrical appliance develops a fault in which the live wire touches the outer casing of the device, you could be electrocuted if you pick the device up. However, by including a connection between the device casing and the earth, the current can flow directly to earth without going through you. The increased current will also be detected by an automatic shut-off device, which will result in the current being stopped. If we look closely at the graph produced by the voltmeter and we remember the equation linking frequency and time taken for a cycle, we can see that time taken for a complete cycle is 0.02 seconds. Then, using F equals 1 over T, we can confirm that the frequency of AC electricity in the UK is 50 Hz. The standard 3-pin plug used in the UK contains the 3 separate wires connected to it via an insulated flexible cable. The earth wire is always connected to the top pin. The live wire is connected to a fuse before entering the bottom right pin. This acts as an additional safety device. If a fault in the device causes a huge current to surge through the live wire, the fuse wire will melt and therefore break, and so disconnecting the circuit. The plug itself is made of a protective hard plastic, which is insulating and durable, which means very hard wearing. The pins are made from brass, which is a hard alloy of copper and zinc. They won't rust, and they're very good conductors of electrical current. The fuse in the plug, as I've said, is designed to melt if the current becomes too high. Different fuses melt with different currents. The fuse rating shows the maximum current that the fuse will allow before melting, so should be carefully chosen for each appliance. You want a fuse with a rating high enough to allow the normal current to pass through, but not so high that it fails to protect you in the case of a fault. The earth pin is the longest of the 3 pins. This is so that it's the first pin to make contact, ensuring the device is earthed before the live pin is connected. If you look closely at the wall outlets, they have protective covers over the live and neutral sockets, which only open once the earth pin is pushed in. This prevents people from inserting objects into the sockets and receiving an electrical shock. Some other wall outlets from around the world look like they've received a shock themselves. When we use an electrical appliance, the current transfers energy to the device. We could also say that work is being done, since energy is always transferred when work is being done. The power is defined as the rate of energy transfer or rate of work done. The equations for calculating power then are power equals energy divided by time and power equals work done divided by time. Notice the units here because the equations only work when the correct units are used. Energy and work are both measured in joules. Time is measured in seconds, even though the exam may try to catch you out by stating time in minutes or hours. You're going to have to convert this time into seconds before using these equations. So what is the unit of power? That's right, watt. Watt is the unit of power. Power is measured in watts. That reminds me, who are the most powerful people in an office? Those who work overtime. By rearranging these equations, we can calculate the quantity of energy transferred. Energy transferred, or work done, is equal to power multiplied by time, or E equals PT. There is an alternative way to calculate power. We know that current is equal to the quantity of charge flowing past a point per second of time, or I equals Q over T. We also know that potential difference is equal to the energy transferred per coulomb of charge, or V equals E over Q. If we multiply current by potential difference, we can show this by multiplying their equivalent fractions, the Q over T by the E over Q. In this case, the Q's can cancel to leave IV equal to E over T. But we've just seen that E over T is how we define power, so we can conclude that the power is equal to current multiplied by potential difference, or IV. If this is too complicated, you can replay this last bit a few times, or pause the video here. Or don't worry too much about how the equations come about, and just remember them all as they are. You will have to use them though, which means you may have to also rearrange them. We can certainly use these equations to select the correct fuse for a device. Remember, it needs to be high enough to allow a normal current to flow through it, but low enough to melt if the current gets too high. So we have to calculate the normal current. The power of an appliance will be written on a label, often at the back or the bottom of the appliance. Here's one from the bottom of my sandwich toaster. It tells you the power as a range between 1850 to 2000 watts. It also tells us the potential difference of the supply as 230 to 240 volts. So we can rearrange the P equals IV equation to give current equals power over potential difference. Substituting the values, we get current equals 2000 over 240, which equals 8.3 amps. Fuses are usually available as 3, 5 or 13 amps for most household appliances. Given that my sandwich toaster normally uses a current of just over 8 amps, a 3 or 5 amp fuse would be no good. It would blow as soon as I switched it on. I'm going to need the 13 amp fuse if I'm going to actually use the toaster, but the fuse won't blow until a current of 5 amps more than normal flows through it. Still, it's better than not having one at all. Resistance heating is a term which describes the energy which takes place whenever a current flows through a resistance. So thermal energy is transferred to the surroundings. We can calculate the power of this energy transfer in two ways. We've just seen how power is equal to the product of current and potential difference. So if we know the current through and the potential difference across the resistance, we can calculate the power, or rate of energy transfer, to the surroundings. However, we may not always know the potential difference across the resistor. If we remember that potential difference is equal to the current multiplied by resistance, we can replace IR for the V in the first equation to create a new equation which shows that power is equal to the square of the current multiplied by the resistance. This new equation shows us how power is related to current if the resistance remains constant. It shows us that power is proportional to the square of the resistance. In other words, if the current through a resistance is doubled, the rate of energy transfer to the surroundings becomes 4 times greater. This new equation also gives us another way to calculate the current through a resistor. By rearranging it to make current the subject, current can be calculated by taking the square root of power divided by resistance. The formula triangle for this equation can be used if you really need it, if you use P, I squared and R in this way. Then you can see that if you want the current, you'll have to square root P over R. We could also rearrange to make resistance the subject, which would give us R equals P over I squared. Finally, we could arrange the equation to make power the subject, giving us P equals I squared multiplied by R. I've talked about quite a few equations in this video. I'll summarise them all for you in a few seconds, but first I just want to remind you of three more really important ones. These allow us to calculate electrical energy transfers, or electrical work. These equations did crop up in the Calculating Energy Stores video, so if you've watched that, you've seen them before. The first method of calculating electrical energy transfer is with the equation E equals VQ. Then we have E equals PT, since power is simply another way of saying the rate of energy transfer. And finally, we have E equals VIT, since we can swap power for VI. Using the equations is straightforward if you can remember them. Just read the question and look at which quantities you're told and which ones you're being asked for. Let's take this example and show you how to do it. We have to calculate the current through a heater. First, we need to identify the equations given to us in the correct SI units. So we're told the power of 500 watts and the potential difference across it at 230 volts. We then need to identify the quantity being asked of us, in this case it's current. Personally, I'd write all these down including the units so you know where you are. Then we need to select the correct equation which contains the quantity we need as well as the quantities we know. In this case it's P equals IV. We know P and V and we're being asked for I. Finally, we need to rearrange the equation to make the required quantity the subject of the equation. This is where it really helps to know how to rearrange equations. Honestly, if you struggle to do this, please learn how to do it. You can watch my math skills video which shows you how. In this case, we have I equals P over V. Then substitute the values for each quantity on the right hand side of the equation. So this gives us 500 watts divided by 230 volts. Then use a calculator to calculate the result of 2.2 amps. The last thing I need to show you in this topic is how to calculate efficiencies. The efficiency of any process can be calculated as a ratio between the useful output compared to the total input. Inputs or outputs can either be in the form of energy or power, so we can use the equation of efficiency equals useful output energy or power divided by total input energy or power. Efficiencies can be expressed as either a decimal value between 0 and 1, or if we multiply them by 100, they're shown as a percentage. The equation may sometimes need to be rearranged to calculate useful output, for example. I've also seen a number of exam questions which ask students to suggest reasons why the efficiency of an electrical energy transfer isn't 100%. Answers to this question should relate to energy being wasted. For example, heating the surrounding air because of friction between moving parts or flowing currents. As I've said, we've covered a large number of equations in this video, and you do need to remember them. So here's a summary of those we've covered. Like I say, please know how to rearrange them correctly as well. To calculate energy, we have these three equations. To calculate power, we have these three. And you may have noticed though that the first two in each section are just rearrangements of each other. Then we have four equations to calculate current, but again there are a couple of repeats as one equation is rearranged to make another. I keep saying how important it is to know how to do this. It not only saves you time in the exam, but it also saves you from having to remember so many equations. Finally, there's the efficiency equation. My website plutoniumscience.com has a section on revision and shows you a number of ways to remember equations like these. Meanwhile,
they said I won't be able to repair it. They said it'll never work. Well, they're in for a shock.
So thanks for watching. Please make sure you subscribe to my YouTube channel and follow my website for future science content, new material or revision tips. You can contact me on plutoniumscience.com or on Twitter at PU94Science, or just email me directly. Keep up the good work and good luck with the exams. Take care.